Perfect. So, with today's summary on renormalization, we conclude on what I would say the classical part of advanced statistical physics before we delve into more recent topics. That's not to say that you still find lots of recent publications on RG methods and even investigations of the Ising model. Don't get me wrong. You will see why next week. Okay, so let's start with a summary of last week, week 11. So we looked at the renormalization group, transformation in general. So the recipe consists of doing some rescaling, blocking, force-graining, however you call it, and then making sure that the partition function is still of the same form when summing over the new spin states as prime, where now the energy E goes to E prime. And from this reorganization of the energy, we can read off a rescaling of the system parameters that I will in general denote as the following. So if I have n parameters k, k1, k2, and so on, some functional dependence of them. So implements this next.
Oh, it's probably about this free mag.
Okay, maybe one of the connections is a little. Oh, maybe no. That the so upon performing rescaling once, or like n times, and then for the n plus 1 time, there's a function that maps the system parameters onto the next system parameters, and that defines our renormalization group transformation. Now, with this in mind, the idea was to study the fixed points, which are defined by the points where the parameters map onto itself. So now this function maps exactly those parameters onto itself. And with this in mind, we can define rescaled systems parameters that go with a hat that now denote the difference of the parameters from the fixed points. So with this, I can measure how far am I away from the fixed points, and now I can linearize my functions around the fixed point with this k hat being small. So what this means is that I can now write my ki hat n plus 1 as a matrix aij acting on the ki hat n, where the aij's are defined as the gradient of fi depends on with respect to kj, evaluated at all of these at the fixed point. So I'm doing a Taylor expansion of my functional mapping f around the fixed points for the distance to the fixed points being small. And so at the fixed point, the linear term of the Taylor dispersion vanishes by definition of the fixed point. And so that's the first order. So this is basically the recipe to linearize around the fixed point. And now what I can do is I can realize, okay, I have a matrix here, so I can expand the matrix in its eigenvalues and eigenvectors. And since it's not a given that this is a real and symmetric matrix, I make here the choice to use the right eigenvectors for the expansion. And with that, I can also expand the system parameters directly in terms of this new coordinate system set up by the eigenvectors of the matrix A. So then my Ki hat n, I expand in UK, just the new coordinate transformations set up by the right-hand eigenvectors. Oh, sorry. This has to be some right-hand eigenvectors of our matrix A. And then I can see that if I now, what it means to perform the successive renormalization group transformation means that I'm acting with the matrix A on my parameters, but acting with the matrix A in its eigen space just means that that I'm multiplying with the respective eigenvalues. So means that this gives me lambda k to the n u k 0 ak. And so this now leads to a lot of insight, because it tells us that actually the magnitude of the eigenvalues now really determines the behavior. And so we're interested in two kinds of behaviors. One is where the magnitude of the eigenvalues is smaller than 1. These are so-called irrelevant variables, because they lie within the basin of attraction of the fixed point and will always flow towards the fixed point. And that's in contrast to the eigenvalues that are bigger in magnitude than 1. These are the relevant variables that derive dynamics away from fixed point. So these are the variables that really need to be finely adjusted to be set at the fixed point to obtain the critical behavior that we observed at the fixed point. And so the image in mind is that if this is our fixed point, then the irrelevant variables the eigenvectors lie in the basin of attraction that I'm spanning here. This is the basin of attraction, and drive flow towards the fixed point, and these are the relevant variables that we need to be adjusted and drive system away. Now, why is this important? As we will see that we can now derive scaling relationships for the eigenvalues and how they scale as the parameters of the systems, focusing on the relevant parameters. And we're going to see that eventually what really drives, this is all that drives the critical behavior, like this emission. And so all of a sudden, independent of what kind of system I start with in the equations that I write down, in the end, I'm mapping it down to the small neighborhood around the fixed point. So I find a fixed point and I have a set of eigenvectors that are defining what is the dynamics close to the fixed point. And this alone sets the critical behavior and also defines the universality classes. So you can now find very, very different systems, but just by what sets the dynamics, this behavior near to the fixed point is the same. And so they all of a sudden, now it makes sense that I can find this spread system to have the same universal scaling as they approach criticality. And to derive the scaling, we started with the answers that these eigenvalues scale as b to the d to the power of ck, where these ck are the critical exponents of the relevant variables that I can also define as ln lambda k over d ln b. Having in mind that what I'm doing in my blocking transitions is that my number of lattice spaces goes b and b minus d, depending on the dimension. And similarly, my reduced free energy scales b to the d. Okay, so that was the reduced free energy. And now we derived that these critical exponents now allow us to really derive the critical exponent of our thermodynamic variables just as a function of those. And so that determines is alpha 2 minus 1 CT, with here using CH and CT to denote the first two critical relevant variables in a system where I only have two relevant variables. And taking them together, we also found these equalities of the critical exponents to hold. And really now we see that it's just these CKs that determine all the critical exponents. They all follow from that. And that's really just about like what is the scaling under the RG transformation as I have to tune my relevant variables. So, and then the universality classes are defined as a critical surface of Wesson protection containing the fixed point. And then to apply this framework, we also looked at the Gaussian model, which is defined as, integral d it's just Landau-Ginzburg up to fourth order. And here's the fourth order and implied field. And so why did I choose this example? Because here, if we go to Fourier space, which means that we're looking at the dynamics in the Brillouin zone, which I'm here sketching for 2D. We see from the Fourier space that there's a singularity at Q equals 0 that's determining the behavior. And so what I can do to solve the Gaussian model directly is to simplify the integral over in Fourier space over the Briand zone by introducing a hypersphere of radius lambda. Oh, sorry, that's meant to be a big lambda, not an omega. And then this can be solved directly, given that we dynamics are governed by the behavior around the singularity. But it's also a nice example of how now the renormalization group transformation we perform in Fourier space. So we perform a blocking now to go down to lambda prime as lambda over b. This is the renormalization group post-graining. Fourier space. And with that in mind, we arrive at renormalized partition function. And from the renormalized partition function, we then determined the scaling from the two assumptions, namely that the fixed points, the singular point, maps onto itself. And that the Hamiltonian stays invariant. And so this rescaling, what we found looked something like B minus D Z T H Z H in the two relevant variables. And indeed, with the singularity at 0, sorry, doesn't need T equals 0 and H equals 0, it maps onto itself. So that's the fixed point. And then from the invariant, the Hamiltonian needing to stay constant, the coupling looked like Z squared B minus D minus 2K. And from this condition, we find that Z, the rescaling of the magnetization in this case, needs to be B plus D over 2. And then inserting this back into the scaling, we can directly extract the scaling of the relevant variables, namely B2 and H B minus D half H, so which means that CT is 2 and here HT is 1 plus D half, and then all the critical exponents follow. And so that's a example of how we can really now very efficiently use the renormalization group framework to solve the critical behavior that beforehand was out of, well, in this case, we could solve it directly, but, you know, just for the sake of showing that this was still shorter than going through solving the integrals in the hyperspace. Yeah.
Why did I want to, why should K stay invariant about, for example, L, the other coupling constant? Because
yeah, so L the case to 0 under this transformation. So we have that's something that we checked, right? That the higher order becomes less and less important. If we would have found that under this transformation that we chose here, L grows, we should have to reconsider, right? Because then obviously L becomes the more important parameter as we approach criticality compared to K, and then we should take care of L staying invariant. So the goal is that the Hamiltonian stays invariant, and it's trading the the course, like having a look at all the parameters of how important they are.
Oh, okay.
Okay, and so now this concludes the chapter on randomization group, and for the remaining, I think it's just 3 weeks or so, weeks, I chose to teach you more like modern topics of advanced statistical physics that sort of really, I mean, by now they are sort of on textbook level too, but I still very much topic of current research. Namely, we're gonna today delve into polymer physics, and in particularly look at flexible polymers now, and look into the freely jointed chain model. Why do we care about polymer physics? Well, you will find that actually polymer physics is important, and I will take this angle for a huge plethora of processes in life, because polymers are the building blocks of, like we can, our DNA is a polymer, a lot of building blocks in the cells are polymers, but it's the same is true for any soft materials. That's the same true. Like, if you go to Christina Papadakis, who's measuring, you have a whole plethora of different polymers that we use in our everyday life. And the physics, particularly of these polymer melts, can be still very challenging, and we can't really still needs a lot of investigations. My angle is to look at filaments in the cell. And so just to motivate why I care about polymer physics. And so like linear polymers, and also that, where you have a chain of elements. This is what we will focus on physics-wise. So these are constructed from individual monomers, or monomeric units. That's what I have here. To form an unbranched chain. So let's focus on those. For example, a counterexample would be the polymers that making up the membrane of the cells. You might have seen that before, like, how does a membrane that is the first start that we need to have in life, right? I mean, so to have life form, we needed to have replication of information. But we also had to have this being enclosed in, some kind of compartment, such that, we can define entities that then reproduce. And so these membranes form, for example, because you have a hydrophilic head and a hydrophobic chain. Sorry, me and chains. And then they form a phase transition in water, where they line up in specific structures. I believe I showed you like the very rich phase diagram of these of membranes that can form. And so typically these, for example, they can have multiple branches as well. So you can have kinks, specific kinks, and which mixture of which polymers you have really determines the mechanics of your membranes and what they can do and what they can't do. That's very rich and still, very much not understood. But okay, but we're not going to worry about them. We've got to worry about the linear ones, of which we have plenty already. Just as another mean of definition, the monomers don't need to be identical. To be and may themselves not only they don't need to consist of a single atom, but they can be constructed of more elementary units, chemical units. So the key is just that they have a repetitive structure a repetitive structure. First example of such a linear polymer that is very crucial to us being here is our very own DNA that is formed into a double helix with 2 sugar base phosphate strands with a length along the helix of 0.34 nanometers per base pair. And a molecular mass per unit length of about 1,900 daltons is the unit to measure chemical in mass nanometers. We will use this for comparison. So DNA, as we're going to see, it's considered to be a very flexible polymer, which we can already see from the individual units are very small, and it's very lightweight, and so it's very easy to bend. Our body actually invests a lot of machinery to bundle this very flexible coil up in our body so that it's organized. But you can think about your DNA as the cord of any electronic device that you didn't nicely wrap up, but you just put in a place. Take the cord of headphones, right? If you just put them in a pocket, what will happen? You have a whole mess when you pick it out again, and you really spend lots of time to disentangle it all the time again, and you're wondering, why did this happen? If you take this picture, this is a good example of what your DNA will do. And indeed, if you, for example, look at bacteria, which don't have such a sophisticated machinery to nicely call up the DNA, you will have such a mess of, basically at least how it looks like in these entities. Little more structure you can achieve when now you don't take the cords of your earphone, but you say take the cord of some bigger electric wire. This won't happen, right? It won't happen that it will end up in such a messy coil that you really need to unknot when you dig it out. And why is that? Because this is stiffer, so it's not as likely to bend up and curl when you just tuck it into a pocket. And you will also need a lot of more force to tuck it into a pocket because you actually physically have to bend it. And this is a good example of the skeleton of a cell. So you have a skeleton, which is made of bones, which gives your body the shape that you have. And every single cell that you build off also has a cytoskeleton, a skeleton within the cell, which is built of polymers that give it the shape and the mechanics, and also, for example, the protrusion forces, the forces to migrate and do things. And so that's why the second part that I want to motivate are the principal components of the cytoskeleton. Of which we have three, sorry. There's actin, so-called intermediate filaments, and the microtubules. If you want to have an image in mind to remember the names, actin, this is basically what your muscles are made of, key building block to generate forces. And in your muscles, this is really the polymer that's really nicely aligned up and organized to generate forces. Microtubules, these are the polymers that are responsible for coordinating cell division, for example. So they the tracks that nicely untwist the calls of the chromosome and make sure that they divide. And intermediate filaments are a very hot topic because we don't know so much about them. Each of these are composite structures made up from protein units, subunits, and each of which is a linear chain of hundreds of amino acids. So when I was talking about individual monomeric units, these are now like full-fledged proteins that in itself consist of lots of amino acids that are lined up and bundled up in these protein units. For actin, the building block, this monomeric unique, is G-actin, where the G stands for globular. And this consists alone of 375 amino acids, just to give a scale. And has 4,002, sorry, just put this there. And 4,200, no, 42,000, sorry, Daltons as molecular mass. And these monomeric, these globular actins are now assembled into a string that is called F-actin, where here now the F stays for filamentous. And it's a little bit that they also curl up in a very shallow helix kind of form. Let me try to draw this. So you have, in a sense, this would be one. So each of these circles is now a globular actin, and they sort of form these strands. And really now these strands, you have to imagine them like being packed up next to each other. And this is what forms your muscle fibers, like the entire muscles. This is really the building blocks. So this is a G-actin. And here we have two strands forming a cord. But that are individually, these cords are metastable. So they can, something that we won't go in, but what is cool about the cytoskeleton that it can be very dynamic and adapt, which you may also know that because you can train your muscles, right? You can change these fibers, obviously. And so here now we have 16,000 Daltons per nanometer mass per unit length in these strands, and a typical actin concentration monomer, oh God, concentration in the cell is 1 to 5 milligrams per milliliter. So it's really, really rich. And the key you know, given that we don't know so little about the intermediate filaments, but it's to all our understanding, it's really what makes the dynamic mechanical properties and shapes and so on of our cells. Intermediate filaments have a different structure. They are slightly wider than F-actin. They also have a more complex hierarchical structure where we have two protein chains intertwined into a helix, and then these two, and then such a helix, two of these helixes, and two helices are then paired side by side to form a so-called protofilament of 2 to 3 nanometer, not millimeter, that would be crazy. That's a hair width. And then these protofilaments itself, talking about hierarchical structure, and then you have bundles of these protofilaments. Bundles of 8 protofilaments in a cylindrical shape of then 10 nanometer diameter. And then you can have 4 strand protofilaments bundles, for example. They would have such a molecular weight, so a little lighter than F-actin, or the bigger ones would then be much heavier. So there's more variation in these structures than for actin. And last but not least, microtubules. They are made up of tubulin as the monomeric unit, and of tubulins there's actually 2, so it's present as a so-called heterodimer. Hetero means a dimer consisting of 2 different subunits, and these subunits are called alpha tubulin and beta tubulin. And they now assemble into strands like this, where this would be alpha. Oops. This is an alpha, and this would be beta, and so on. And then they form these, again, protofilaments. And this would be then 8 nanometers. And they really now form into like a hollow cylinder of 13, sometimes 14 protofilaments. And here we go. It's a very heavy And you can think about microtubules as really being very, very stiff. So say this would be microtubules, this would be actin, and then the cord of your headphones would be DNA, just to have like a scale on the mechanics. And so that's why like these microtubules, they really act as rigid structures that if the cell nucleus divides, then these form really sturdy beams along which the chromosomes are tracked apart such that two new cell nuclei can form. And the actin meshwork is really it's really like a very flexible actin meshwork that's sort of lining. So if this is a cell, then the actin sort of forms really a meshwork of bundles, cross-linked and webbed up underneath the cell membrane, and gives the cell its rigidity. And for that, it's just the motivation to why should we care about polymers, and really to understand polymers then turns out to be, again, a statistical physics question, which is hopefully motivating you that so I like to use the term biological physics, so I do biological physics, but in my heart, I'm a statistical physicist. I mean, that's what we do. We use the means of statistical physics to describe life. And I could have as well chosen to describe something else, like magnets. It's the same set of tools. Just turns out there's much more fascinating open questions in life than about magnets. But, up to you, your choices. And I think that's the cool thing, right? That we teach you in physics. I mean, that's why you study physics, right? Because you learn principles, and then you can apply these principles for whatever you're interested. And that might be something else in 10 years' time than now. At least that's what I love about it. Okay, so let's dig in about polymers. And so the first concept we're going to look at is flexible polymers, where you should have DNA in your mind and your wrinkled up headphone cord. And so to describe flexible polymers, the first model that I want to introduce to you is the freely jointed chain, which is an idealized model which nicely captures the physics of flexible polymers, where and allows us really to learn a lot about the physical properties. And we'll see that why we can also gain insight why it's such a good prediction on Friday. So this is a coarse-grained model neglecting the chemical details and the molecule level of degrees of freedom. We only here care about the monomers as being lined up in a chain. So they are lined up in a chain, and that's all we care about. So these would be my individual units, these dots, and these dots that I will call a segment. And in between these segments adding up to polymers, I have a bond of length B. And that's the same bond length in between all segments. That's why we care so much about like having, we don't care about what kind of units, but same kind of units lined up in a chain. To describe the physics of the system, I denote the position of each segment by a position vector xi and so on, x n minus 1 xn. And I take it that there is a free hinge between two bonds. And then the polymer state, so a polymer configuration, is then fully defined by the set of position vectors, or even 1 degree less, by the tangent setting up the direction of individual the tangents T1, T2, and so on, by the set of tangents where the TIs are defined, as being xi minus xi minus 1. We here assume that there's no energy cost associated with the polymer state. That means there is no interaction between segments. Like there's no electrostatic repulsion or whatsoever, which means that these individual tangents are statistically independent, right? So that means that the tangent orientations are statistically which means that Ti and Tj with I unequal j, so two different tangents, if I just take them and there's no interaction between them, the correlation should be 0. And there's also no energy cost associated with the subsequent orientations. So there's no limitation of if I have a segment that goes like that, then I have a preferential vector for the next one. Why is this a statement to make? It's obviously different here, right? You can tell me that if this is the tangent describing the bond here, then it's very unlikely that this next tangent goes like that, right? That I need a lot of force to make this happen, and I can't even make 180 degrees, right? So there's this is not statistically independent, this setting. For ear cords, headphone cords, this is true, or this is a too good approximation too. On a certain length scale, like you're very likely to bend backwards, and that's what gives rise to all this knotting. But here, as I said, like we have the very flexible, and there's no energy cost associated with the orientation of subsequent tangent vectors. This is the free hinges that I refer to. And from that, we can actually infer the probability distribution of the tangent vectors. because it means that, so there's no energy, so they are all oriented in three-dimensional space. So the probability distribution is of an individual tangent is just normalized by the surface integral over a sphere, which of a sphere of the bond length b. So, and this is 4 pi b squared. And the only caveat that we have is that the tangents need to be exactly b of length by definition, or bond lengths. So this is here a uniform distribution on a sphere of radius b. And from that, we can then get the probability distribution of an entire polymer state, because it is just defined by the set of tangent vectors, right? So the probability distribution of a polymer state is then psi of the whole set of tangents is then just the product of all individual ones, which is then 1 over 4 p squared product I to n delta ti minus b. Now you can see why it's beneficial to have a very simplified model, because we can nicely write down the statistics of the system. I'm very aware that we here also neglecting excluded volume, right? That we had this when we discussed gases, that in principle individual segments, so the individual monomers can't be in the same place because of just mere steric interaction. This is a fact that we exclude here, and the results comparisons with experiment justify that. And in particular, when we next week turn to these stiffer polymers, it's perfectly fine because they won't ever meet, because they are actually it's such a stiff system that it's very likely to overlap. But you can see that even for a stiff polymer at long distances apart, that you can run into this steric interactions. But these are really, really hard to deal with analytically. And this is what you need simulations for. That's why we had the whole week on Monte Carlo simulations that you need here. But back to like the beauty of what we can do analytically, and here we aim to characterize the macroscopic state of this polymer chain. And so we characterize the macroscopic state of a polymer by the so-called end-to-end vector. We'll have it revisit multiple times. So what does it mean? An end-to-end vector is the vector between the first and the last segment, monomeric unit, that I denote R. That's the end-to-end vector. In equations, the end, oops, wrong color. I feared that. The end-to-end vector are defined as xn minus x naught. I can basically write as summing over all the tangents in between, right? Just go back quickly. So if I just add all these tangents subsequently, this gives me the end-to-end distance. And now we're interested into the mean, so the average of these tangents, and because of the uniform distribution of all individual segments, the sum over all of them is 0. So as all orientations are equally likely, and I have anti-parallel bonds cancel each other. So if I have a bond in this direction and an opposing bond, they cancel. And so statistically, the mean of the end-to-end distance is 0. But we can actually measure the size of the kind of coil that your headphone cord ends up in by the second moment. So that would be then r squared. And here we arrive then as I to the n ti squared, which is I equal n j to n, and now we have ti, tj. We know that they are uncorrelated if I and j are different, but if I and j are the same, then I'm looking at the tangent squared, and the tangent squared is just the length of the segment B squared. So this is then delta ij b squared. Delta ij, subsumming one of the sums, having one left, gives me n b squared. So we see that the extent of a polymer, taking the square root, scales with the individual segment length and square root of n. Where here now the segment length contains all the microscopic details of our chemical, and this is a general mesoscopic here, referring to on length scales bigger than the chemical units, law that holds. And how can we interpret this now? Well, what we state here is that there is no interaction, no energy cost associated with the whole system. So what we're looking at here is really a system that's fully governed by entropic forces, right? This is just the entropy of the system that gives rise to the call not being in a single collapse to a single point or being ordered to some degree, but just being of like some entropic order in general size. And indeed, this scaling will turn out, and we'll see why, to be a very general law for the extent of polymers. So since all states have same energy, this is governed by entropy alone. So like a fully stretched state very unlikely. Okay, so the end-to-end distance seems to be a good observable that we can handle nicely. And so we'll dig into a little more to derive the probability distribution of the end-to-end vector. And so how can we do this? We can define now the position of the nth segment only as only dependent on the position of the n minus segment and the orientation of the tangent in between. Only dependent on the position of the n minus nth segment and the tangent in between. So that means that I can write the probability of the end-to-end vector of the nth segment as integrating over the probability of the nth tangent vector that is given by our probabilities distribution we wrote down beforehand, and the probability of having an end-to-end distance r at the n minus first segment. So this is summing over all allowed values of Tn, and that's the probability distribution. Tn. And with copying down from above, this probability distribution being given by 1 over 4 pi b squared delta of Tn minus b, sorry, minus b. We then get that P and R is equal to the integral over the surface of a 3D unit sphere, which I write as the omega. I'm going to find in a moment. So this is a vector on a 3D unit sphere that I'm summing over, and this sum is then going over d5 from 0 to 2 pi and d cos theta from -1 to 1. This is the definition of the 3D unit sphere. Now to simplify this expression, we Taylor expand for the limit that we have a lot of monomers, so n large, and the end-to-end distance r being bigger than the segment length b. Sorry. What I didn't do is that I said, I'm sorry. Okay, so this is, okay. So here I'm summing over the distributions of the distance t, but that means that I take the probability distribution of P of n minus 1 r minus that segment is missing, right? To be equivalent to this, sorry, Tn. And then in this, now performing this integral, I put in that Tn is of length b, and then here, I'm sorry, this becomes b and the vector omega. And now we have the vector there, and that's justifying what we not only have to expand for n large, but also for r bigger than b. Otherwise, this doesn't make sense. So we expand r minus b omega for n bigger than 1 and r bigger than b. That means that I write this Pn minus 1 r minus b omega as 1 minus delta ddn minus b omega alpha dd alpha plus a half b squared, sorry, 2 components, alpha beta d alpha d beta, and so on, acting on Pn r. And now if we insert this here, then the integral over omega for the constant term gives a 4 pi, which cancels here. So this term here, this one cancels with the left-hand side. And so I arrive at a differential equation for P of n of r defined by those terms. So having cancelled this one term, I get 1 over 4 pi, and now we are left with minus integral d omega v dn of P of n and r minus b d omega alpha and last the square term d in the first integral, we're taking derivatives to check to n. This whole function does not depend on the vector omega, so I can integrate this part and it gives me a 4 pi, which then will cancel with this term subsequently. If I look at the second term, we're here integrating over the whole unit sphere and mapping out a specific direction. Again, this is independent of omega, so it's just looking at this integral here. But since the sphere is symmetric, and so I'm summing over antiparallel directions over the whole sphere, this integral is equal to 0. And it only is different if I now have the 2 vector components, because now if they align in a specific direction, then I get the contribution of 4 pi over 3 if delta alpha delta beta. And so we then get from this term, if I move this to the left, this term, so the minus goes away, and I get dn of P of n r is equal to, I have a 4 canceled here, so we are left with a 2. 2. Sorry, that was stupid. And it's so I cancel the 4 pi with those 4 pi, and then I get 1 over 6 is left. So, and then I have here b squared over 6, and delta alpha beta means that I get the Laplacian here of p of n and r. And so this is now the differential equation describing the probabilities distribution of the end-to-end distance vectors. And that really strongly reminds us of, like, this is the kind of differential equation that we know, because this is a diffusion equation. This is a diffusion equation of effective diffusivity b squared with 6. To solve this diffusion equation, we also have to supply an initial condition. The initial condition is P of N0 R is a delta function. And then the solution follows. Normalization factor of 2 pi NB squared. Which is the Gaussian distribution. And so this is really a very insightful result, because we learn which parameters of the system really govern the dynamics. So initially we started out with a polymer, and so the two, I would expect the polymer to be governed by the intermonomer distance, the segment length b, and also the overall length of the system, which is n times b, right? These should be the two length scales that should impact the configurations and the state space of the polymer. And now it turns out that if I look at the probabilities distribution of the end-to-end vector, that there's only one quantity popping up. There's only this one factor, which is NB squared, which we know already because that's the mean end-to-end distance vector that's popping up. So note that and p squared alone fully characterizes statistics polymer states instead of the two intrinsic length scales be the bond length and L and B the total length. So what does it mean? Like graphically speaking, we find that the probability distribution of the end-to-end distance vector is a Gaussian, and it means, and also that the mean end-to-end distance squared scales with the lengths of the system NB, L and B, with the slope of 1. So this was, we arrived at this very central result by mapping the probability distribution to the diffusion equation, and that we were very lucky to, because we know the solution to solve. because we didn't have this so far in this class, I would also like to show you an alternative approach to arrive at exactly the same result. Just to remind you of these different strategies to solve probability distributions being available, namely to use the methods of characteristic functions. So an alternative solution strategy is via the characteristic functions. So that's quite a while ago, but remember from your statistical physics class that the characteristic function is the Fourier transform of the probability distribution. So to see characteristic function index n, now depending on the wave vector k, is therefore the integral, the Fourier space, Fourier transform k r of our probability distribution of the end-to-end distance vector. And so if we have this Fourier transform now acting on our previous equation where we wrote Pn of r as a function of the, normalization missing, the integral over the unit sphere surface of the probability of n minus 1 being at r minus b omega, we find that, and I want to, this was our previous equation, but now I want to change the nomenclature just a tad by making this n, and then this becomes n plus 1. Because then we have here P of n inside, and this means that I also have a plus here. So n plus b of r omega then gives us the n plus 1s. Sorry, no, the plus, that's stupid. It's a minus. And then we can define the Cn plus 1's characteristic function as now performing the Fourier transform, the omega r. So E minus I K R. And to solve this, I'm going to define R prime as R minus B omega. So that my integral over omega, so this changes then the exponent to R prime plus B omega. And so if I pull out the exponent, then I have E minus I B K omega. And here we're left with the dr integral, the minus I K R prime, R prime. And now with this transformation, this becomes the R prime. So that's Pn R prime. So this is just as before, Cn of k. And this integral here, this is, we can solve, or we should solve. What we get here is, these were the integrals from 0 to 2 pi. Let me drag on the normalization d phi. from -1 to 1 of d cos theta. And then I can write this exponent here as bk cos theta. And that integral we can solve. Normalization with 1/4 pi. First integral goes at 2 pi. And then the second integral over d cos theta gives me 1 over minus I bk e minus I bk minus plus I bk. And that's then sine bk over bk, with the two summing up in the and so we find a relationship stating that the n+1's characteristic function is sine bk acting on the nth characteristic function, and if we continue, if we solve this relationship iteratively, we arrive at the characteristic function being defined as Cnk, being defined as Cnb sine bk over bk to the power of n. Now note, with this approach of the characteristic functions, we so far did not make any approximation. And that's a difference to the approach that we had before, because what we did here was we Taylor expanded. We made an assumption on n being large and the end-to-end distance being bigger than b. So we have to keep this in mind. And the characteristic function in this case allows us really to find an exact solution for any choice of parameters. So this is the exact. Here an exact Fourier back transform is possible. No approximations. But again, you trust me that doing this exact Fourier back transform of the sine is not fun, and it gives rise to very clumsy equations that I don't have fun writing down here, and you don't have fun copying down. And so we'll make the same here now, approximate also in the limit of n to infinity and b being small, to perform easily the Fourier direct transform. But again, to highlight, it would be possible to have it the exact result and have the exact end-to-end distance using this approach. And so with that, now using this approximation here, we want to look at the limit taking n to infinity and b to 0 over bk to the power of n. And to that end, we expand the sign for b small, or this sign bk over bk, to get the 1/6 bk squared plus higher orders to the power of n. Note that the mean square end-to-end distance was b squared n, and we want to keep that one constant when running b to 0 and n to infinity. And so to do this, we rewrite now when taking the limit n to infinity, we write the b squared, we expand with n to get r squared k squared over n plus higher orders, the n squared. And now this limit performing the limit n to infinity, keeping the end-to-end squared end-to-end distance vector fixed, we find an exponential of r squared k squared that is easy to back transform and gives us the previous result. The back transform, we arrive at the previous result. It is actually no surprise that we arrive at a Gaussian distribution. We could have actually stated that without doing any math. Because what we're doing here is that we have a set of independent variables, the tangents that we're drawing from a uniform distribution on the sphere, and having identically distributed independent variables, we should have in the limit of n large, the central limit theorem already tells us that we should arrive at a Gaussian distribution. And this actually makes these results so central and allows us to justify why we are actually very successful with such a simple model of the free Lagrange chain. Because we know that the central limit theorem is true in all cases if even if our independent variables have short range correlations, we'll always in the limit of n large arrive at the Gaussian distribution. So we learned that even though we shoved a lot of chemical details under the rug, this result is very should always be true for n large, because the central limit theorem is true also for short range correlations. So the Gaussian distribution so follows. Theorem as R is the sum of identically distributed independent random variables. And since the central limit theorem also applies for random variables. With short-ranged correlations, the Gaussian distribution is also valid if some energetic cost is associated. It's subsequent bond orientations. Only need n large. So this is a very universal law, and justifies our simple model. And with that, I would like to thank you for your attention for today. And on Friday, we'll dig more into the freely jointed chain, and we'll build on this Gaussian distribution to derive universal laws of flexible polymers. Thank you.